Ari is an immersive applications developer in the XRCC team that we talked about earlier. Her career in computer graphics and XR goes back almost 30 years. Past employers include Industrial Light and Magic, the U.S. Naval Academy, Leidos, and several startups, including two that she co-founded. Her VR work has included simulated experiences for submarine crew members and for rats. Ari earned her PhD in computer science from UMBC in 2018. She joined APL in 2019 and then shifted to the XRCC in 2020 because, as she says, we have the better toys. Over the last couple of years, she was the VR team lead for the DARPA ACE project. And today, she's going to talk about the display technology that makes it all possible. Please welcome Ari to the stage.
That's assuming I can figure out this technology. Here we go. Yes, no? There we go. Okay, so the inspiration for this talk came from the constant flood of new hardware hitting the market. One estimate I've heard is that there's a new headset coming out approximately every 90 days. Sometimes it feels like even more than that. Just in the time since I submitted this talk for review, the Vision Pro has come out. We've heard that the Quest Pro is stopping. There have been other developments, new announcements. It's this huge flood of jargon and numbers, and ours is better at this, and it's a new version of that. And for me, especially coming from more of a math and theory background, what the heck does all of this mean? Which one is the right choice for a particular project that I'm working on? What numbers do I actually care about? How does this work? And so I started organizing all of this for myself and realized that this was probably going to be useful to a lot of other people starting to get into this industry or trying to stay on top of that constant flood of new releases. And I found myself constantly asking a couple of big questions. The first one is, what is whatever the new feature is? It might be a new version of an existing feature. It might be a better technology for an existing capability. It might be something totally new. The next big question is, why would I want it? And when I say, why would I want it, sometimes that means, why do I personally care about it? Things like improvements that allow me to not wear my glasses in a headset. And other times the I is more the project or the sponsor or the activity that I'm currently supporting. And often the answer to that boils down to, I would want it so I can see more, so I can see better, or so I can see more easily or more comfortably. And then the last big question is always, what devices have it or will have it, or who's working on it? Where am I going to get this feature? Okay, so let's dive into it. The first number that we tend to hear about is always resolution, number of pixels. This big bright chart is from Wikipedia. It's the per eye resolution, the pixel count for various headsets. And this image is a little bit old, so I've listed pixel counts down the side for some of the more recent headsets, and they all pretty much fall between the gray box and the dark blue box, the Oculus Quest 2 and the Vive Pro 2 within that diagram. So they're not breaking earth-shattering new ground. You'll notice that there's a couple of unusual outliers here. The light blue box that's much wider than the others. This is a couple of different models of Pimax headsets. They're known for super wide displays with correspondingly high pixel counts because they're covering so much larger area. Now, the question of covering larger area with a given pixel count brings us to the next feature or spec that you want to pay attention to, because pixel count doesn't tell you the whole story. You spread the same number of pixels over a much larger field of view, you're going to get blocky. You're going to not be able to see what's going on with the detail. It's not going to seem realistic. sometimes what you're more interested in is the pixels per degree, and that's degree of your visual spread. As a general rule of thumb, the higher that pixel density, the better the realism and reduced screen door effect. What that means is, if you take a look at this picture, this is the same part of the same interface of the same application seen through two different headsets. The one on the left is one of those Pimax ultra-wide with a very high resolution. The one on the right is the HTC Vive, the first generation of that headset, and it has far fewer pixels spread over that same part of the image. So it looks like you're seeing it through a screen door. It's blocky and choppy. You can still see all the... Most of the recent displays have a field of view that's about 100 to 115. I mentioned the Pimax headsets. They're huge. They are in the order of 200 degrees. Listed a couple more down the side here, some recent or familiar headsets. The Pro 2 has 120-degree horizontal field of view. And usually if only one number is given, it's the horizontal field of view, but you'll also see vertical, you'll see the diagonal. Sometimes they don't tell you which one you're listing. It can be a little hard to make sure you're comparing apples to apples. The Pro 2 PPD, pixels per degree, comes in at about 24.9. The Quest Pro, 22. And the Vario XR3 and VR3 headsets, they list two different PPDs. For the Phobia, it's 71, which is just earth-shattering if you look at the other two that I've listed here. And in the periphery, 35. Okay, so you're probably asking, why does this one headset have two different values? That gets us to another aspect of headset rendering and features, which is the idea of the phobia. This comes from human vision. The human vision system has a small region in the center of where you're looking that is very high resolution. And we're not even aware of how small that is and how much better it is than in the periphery of our vision. Our brains are kind of filling it in so that we think we've got high resolution everywhere, but we really don't. So foveated rendering headsets take advantage of that. Why put all the effort into rendering clearly out here where I'm not actually seeing it right now? So some systems, this is fixed. This is in the center of the display. There may actually be two different displays, one with a much higher resolution than the other, and that's what's going on with a number of headsets. There's then the next level is dynamic in resolution, but fixed in location. So the level of detail that's in that fovea region can vary depending on how much you're currently stressing your GPU with other aspects of your VR or XR activity. For example, if you've got a really high-intensity water simulation going, you don't have as much GPU available for rendering. So even your fovea region may not be as high resolution during that point in time. Another aspect of the headsets that you'll hear a lot in the marketing is what is the display screen technology. So going back a little way, everything was LCDs, and the idea here is that you've got two layers. There's the one with the colors and the one with the light. And so the light source passes through the colors and you get your image. The problem there is if all the pixels are sharing one light source, it's really hard to get an honest-to-God black, right? There's always light coming through. You can make the color be dark, but there's still a light source active behind it. The next technology, the OLED or organic LEDs, here the pixel and the illumination are all in one. So with that many different light sources, it's not as bright, but you get that individual control of brightness per pixel. So you can actually have black. You can have a pixel that is truly turned off. And that makes a huge difference in the contrast range that's available, the brightness range that's available. It looks really nice. Now, it does have problems with smearing, because if you turn it completely off, it takes a little time to come back on. It's like preheating your oven. So for some small period of time, it's not quite at the right brightness level. But these are thinner, lighter They're more expensive to produce, and they have a shorter lifespan in general. These are very blanket comparisons. But those black levels are gorgeous. What we've seen in a number of recent headsets is that they've actually switched back to the 2 layers model, but with improvements in the lighting layer so that it's not one giant light source, but rather many smaller ones. Still far fewer than the number of pixels, but for example, one of the recent headsets, I think it was the Quest Pro, it's roughly 500, and we're talking about thousands of pixels. So you get an effect called blooming, because if one pixel is on, its neighbors can't be completely dark, but it's still really nice. Some other display specs to look for, you'll see refresh rate. Typically, you'll see 90 hertz or 120 hertz. Some headsets can do both of these. Some offer other refresh rates. They vary, but it's generally in this range. And something to keep in mind is that you want to think about this in tandem with the resolution. If you're pushing an enormous number of pixels per eye, per frame, and you increase how many frames per second you're doing, then you're asking that much more of your GPU. This is why the standalone headsets tend to have a lower resolution, although I wouldn't say that's anywhere near a black and white division. And for tethered systems, this affects your connectivity. What data format do you need to push all those pixels? What wires do you need? Do you need more than one video cable to handle all those pixels being pushed from the rendering machine to your headset every frame? Another display spec that's not generally reported, but you can find it if you look for it, is the binocular overlap. Typically, a headset has one screen for each eye, but they're not rendering 2 completely separate parts of the virtual environment. After all, human vision is binocular. What my right eye sees and what my left eye sees overlap significantly. That's how we get our depth perception. So what's rendered in the 2 display screens also overlaps in terms of what part of the virtual world it's showing. The screens themselves aren't overlapping. It's what are they rendering. So typically, some fairly large percentage of what they're displaying is visible to both eyes, and then the outer edges of each screen are showing the stuff that's only in the periphery and only visible to one eye. Even more display specs, you won't see screen rotation talked about too much, but this was a bit of a buzz over the Quest Pro because they have 2 rectangular screens, but they're actually rotated inward 21 degrees. And what this gives you is more of a vertical field of view, and it's putting the corners, the additional range where it actually matters. This was not the first time that this idea had been suggested. This was actually patented by Valve for the Deckard project that we never, moment of silence for the Deckard project. Then our last display spec that I want to bring up is peak brightness. This is much more important for AR than VR because with VR, of course, you're completely blocked off from the real world, whereas with AR, the images being displayed are competing with brightness in the surrounding environment. Okay, moving on to lens type. So Fresnel lenses, this is what's used in lighthouses. We've all seen the gorgeous concentric rings of glass. It can also be what you see in the left side of the top image there with multiple kind of jagged rings on a single piece of material. But overall, it's built of multiple concentric rings, so it uses less material than a conventional lens. It does have some image distortion issues, and I'll come back to those later on. One of the issues, though, with a Fresnel lens that's not a problem in a lighthouse is that you need a long distance between the light source and the lens. This is a problem in front of my face. This leads us to pancake lenses, where we're basically taking that long light path and folding it. So the light bounces back and forth between multiple lens components and therefore takes up a much smaller linear distance. That's great, but the problem is each time it bounces, it loses some intensity, so the result is dimmer. Pancake lenses are not a new idea for XR. They've been used in photography for quite a while, but they're only just now becoming feasible for XR because we've got displays that can produce enough compensating brightness to make up for the dimness of bouncing back and forth at a weight and power and price point that people are willing to accept. Then a third category of lens types is basically everything else. I've pointed to Vario as one example here. They use custom aspherical lenses. These give a wider field of view than the pancake lenses that we're seeing in other headsets, and a wider distortion-free sweet spot in the middle of the vision. They also don't have the ridges that can be visible in some of the Fresnel lenses from those successive circles of material in the lens, but the trade-off is that they're a lot more expensive to produce. Now, what I was saying about the smaller lenses and smaller headsets and wanting to fold that distance and shrink everything down, the picture on the far left is me in an early iPhone headset. This was in the 1990s. This was some work I was doing at the University of Virginia. And you can see how far this thing sticks out from my head, and it was heavy. It was really uncomfortable. And there's no counterweight on the back except for the giant tether of cables, because none of this was standalone at the time. It was uncomfortable. The middle picture is the Meta Quest 2, so this is Fresnel lenses. And you can see it still sticks out a good bit from the face, but definitely less than the iPhone did. And the last picture is the Quest 3 with the pancake lenses, which sits much closer to the face. So you can see the progression, and I'm sure subsequent lens and display improvements are going to be aiming to shrink this down even more, because it makes a huge difference not to have it sticking out from your face, both in terms of just looking goofy, but also the weight and balance and comfort level make a big difference. Okay, I mentioned one of the other answers to the question of why do I want this is making it more comfortable and making it easier to see more clearly. Some of this has to do with adjusting the optics for each user, adjusting the actual lenses and placement of the headset on each user's head. Number one thing that you'll hear about is IPD, interpupillary distance. And a lot more people are aware of what this is than used to be with the recent surge in being able to buy your eyeglasses online. They need your prescription. They also need your IPD in order to make the lenses properly. Same story here. If we know exactly where your pupils are, how far apart they are, then the lenses can be positioned in the right space so that the sweet spot for them, the focus of each lens, is where you actually need it. Getting it wrong is pretty bad. Besides just not looking clear, it's a quick route to motion sickness. So this can be done through hardware adjustment, and you'll see different headsets where you can adjust only to fixed IPD distances, or where you can move it continuously, where you can move it manually, or there are some where you can set it through software. So the image on the upper right of the slide, this is an app that you can get on your iPad for measuring your IPD if you're going to go order some glasses. The image on the lower part is from the PSVR 2. This is the on-screen aid to help you set the IPD for yourself while you're already wearing the headset on your head. And then another physical adjustment per user to help get the lenses in the right place for the best clarity is the lens distance to your eyes, literally sliding them in and out. So on some headsets, the front of the headset slides in and out. Others have snap-in frames or magnetically clip-in frames to give you more space or less space. Varifocal lenses have not really hit the mainstream yet, but the idea here is that with your lenses, there's a fixed focal distance, and that means that objects that are up close especially for older folks, are harder to focus on. If the display can actually change the focus distance, then objects that are close up can stay sharp and detailed. That gives us better fidelity to how real vision works without the eye strain of trying to focus on things that truly aren't being displayed at that location. The flip side is that to do this, we have to know where you're looking. So this requires eye tracking, and it requires fairly complex optical hardware to be able to respond to what the eye tracker is observing about where you're looking. So I'm expecting and hoping that this becomes much more readily available in future headsets. One thing that is available currently in a number of headsets is adjustable diopters. The video that you're seeing in the lower left has adjustable rings on each eyepiece. So you take your glasses off, you put the headset on, and you turn the ring until things are clear. Now, as you can see, there is a maximum value on there, and I pretty much max it out. But I'm hopeful that they'll expand that further. And if that doesn't suit, you can also buy prescription lens inserts for a lot of headsets. I have a set for a Vive Pro 2, so when I'm using the headset for a long period of time, I can just skip the glasses. That's not so great for demo environments or environments where the headset is shared among many people, because it's a pain to be constantly changing them in and out. But for a single user for extended periods, it's wonderful. And they're not all that expensive either, so I recommend. I mentioned earlier that the Fresnel lenses have image distortion issues. The answer to that is in rendering. If we know, and we do know, exactly how it's warping the image, then the rendering engine can pre-warp it the other way. And then when the lens does its thing, the result is square. Another rendering capability that's becoming more available, as I mentioned, when we have multiple small lighting units, we can control lighting and black levels independently for each of those units, so we can do localized dimming. And as I mentioned, this results in blooming because we still have more than one pixel relying on each light source, but it gives a much better result than having the entire thing lit by a single light source. And then finally, my favorite thing is dynamic foveated rendering. As opposed to the fixed location, this is using eye tracking to tell exactly where you're looking and do the high resolution rendering there. So it's not necessarily the center of the image. It's probably not the center of the image. It's wherever you're looking. So obviously we need to know where you're looking. This requires eye tracking hardware. But this way you can have the rendering resources focused on that small region of the image where it's actually going to pay off. So I'm going to have a demo set up this afternoon. I should mention that Blake and I both will be in the other room. So not the room that's listed as the demonstrations on the agenda and the website. Basically, we're on the other side of the hallway. It won't be hard to find us, I promise. We'll be the ones with a bazillion headsets so that you can come and try all of these. I've got a number of headsets, both XR and VR, ranging from smaller standalones to some of the very high-end tethered headsets. Just come and try them out. All right, since I've got a few minutes left, I'm going to show you some of the things that you will not see at my demo, but that some of the XRCC folks got to see and try out at a recent conference. Some of the wacky stuff that's out there, and these are in development. So the one on the left is a huge, wide aspect, wide field of view. I mean, look at that pixel count per eye. That's enormous. It's eye-tracked foveated rendering, so the dynamic fovea placement that I was just talking about, auto IPD adjustment, because you can imagine with a screen this wide, it matters where you're looking, where we think your pupils are. The refresh rate at the full resolution is only 75 hertz, but they can do 120 at a lower resolution, and I'm sure they're working on boosting that. The other one here is stitched pancake lenses. I couldn't find a great still that really shows the lenses, but each side, each eye, gets 2 pancake lenses that are sort of seamed together. I'm not sure how much of the seaming is hardware and how much is software, but the end result is that your horizontal field of view is 240 degrees, and the vertical isn't bad either. And this is done by having 4 displays, 2 pancake lenses, 2 displays per eye. So pretty wacky. And that's it for my talk. Be happy to take questions. Come see the demo.
Thank you for that talk. Very, very interesting things to consider. On foveated rendering, something that I've heard my development teams have reported back is that often the time spent to develop and take advantage of foveated rendering doesn't necessarily result in the performance improvements that are worth that time. I was wondering if that's something you've seen in your experience or if that's something that's improved.
To be honest, I have not worked with developing any software that's doing the foveated rendering, but part of the question there is, are you looking at a hardware where the hardware itself is doing the foveation or where you need to control that in software? Mm-hmm. So that might be one answer to not wanting to spend a lot of time developing it, is choose a headset where the hardware is doing it for you.
Gotcha. Thank you.
Hi, Ari. So this is an easy one, but if you had to pick a lens type that's effective and easy for demos with a lot of people with different eyes and glass situations, what would you pick?
A lens type?
Yes.
Off the top of my head, I'd go for a pancake lens, mostly because that's smaller and more comfortable, and that more of the standalone headsets seem to be going with that form factor. For a demo where it's going to be a lot of people with a lot of different visual capabilities, I'd want it to be as comfortable and easy to get in and out of.
That makes sense. Yeah, we've had issues in the past with the Vive where different people have different problems with it.
Yeah, the fewer also something where as many of the adjustments are automatic as possible.
Yeah, less than manual knobs and dials. Makes sense. Yep. Thanks.
Hi, Ari. Great talk.
Thank you.
I wonder if you did any research on AR headsets like the HoloLens or any others.
For this talk, I focused mostly on VR just for the interest of time. We will have, I think we have 3 different AR headsets that are at the demo. And some of the features that I've talked about are the same considerations for both. The numbers and the technology that's implementing them may be different. But certainly resolution is a factor with both of them. As I mentioned, brightness is going to be much more a factor for AR. But no, most of my experience has been with VR headsets, so given the constraint of time not letting me go into all details of everything, I tried to focus on that more.
That's really good, thank you. Given the rapid pace of the technology, where do you see headsets in 5 years? And if you're feeling brave, 10 years?
I think eye tracking is definitely going to increase the ability to put the power where we need it. As I said, the dynamic foveated rendering is one of my favorite features, and that's why, because the driving question throughout my entire career has been, where can we cut corners? And not rendering the stuff you're not seeing anyway is a huge way of cutting corners. So that leads to things being smaller, cheaper, lighter. I think we're going to see a lot of that. What's that? Yeah, we're going to see them, we'll probably see them look like glasses, and we'll probably, just getting back to Blake's topic, we'll probably see AI guiding a lot more of that foveation and dynamic rendering. So, all right, out of time. Great, thank you.